During this lecture, I will derive the geodesic equations that govern particle and photon motion around a black hole or spacetimes more generally from the Hamiltonian Formalism. We have recently been given a new way of probing the center of the black hole at the core of our Milky Way galaxy. The Event Horizon Telescope has provided us with an image that is possibly the most consistent with the data or the radio data they observed via the VLBI of the black hole at the center of Sagittarius A star. And so you can see the reference to the paper here, and here is the image that they view to be most consistent with the data. This permits us to find new ways of probing the matter content of the Milky Way geometry, as well as possibly an observational tool for testing general relativity. This is not the focus of the talk, rather this talk is a means of calculating the geodesic equations, so it's more a technically focused talk. What we will be using is Hamiltonian mechanics. The reason for this is it allows somebody not familiar with all the details of general relativity to actually derive the particle trajectories or the ordinary differential equations that govern the particle trajectories around black hole, as well as the photon trajectories. It also renders the equations in first order form, which is particularly of interest for people trying to apply various theorems from dynamical systems or Hamiltonian mechanics to these equations. Okay, so in some sense this is the most direct entry point to the geodesic equations. And what we'll be using is the formalism developed by William Rowan Hamilton in 1833. So Hamilton was a guy that possibly took all the various approaches to mechanics and canonized them in a method that revealed most of their symmetries that could be found in these equations. And the symmetries he observed can be found in any mechanical system for which you can write down a Hamiltonian. In other words, any mechanical system in which there is net conservation of energy. So the way he does this is we write down a Hamiltonian or a scalar function, and it is a function of pairs of variables, namely the generalized coordinates, and for each generalized coordinate there's a generalized momenta associated with it. And it also includes a time parameter, and for the purposes of this talk I've called it tau, because I will later use time as one of the coordinates itself, as we often do in general relativity. So this parameter tau basically parameterizes a trajectory within your generalized coordinate momenta space. And so we therefore have the Hamiltonian. The qk and pk can be any dimensional vector, and so it's a function of basically the dimensionality times 2 plus 1 independent variables. What Hamilton did was to formulate classical mechanics in terms of a Poisson bracket. So let's just define that rigorously. A Poisson bracket of two functions g and h, which are both considered to be functions of the generalized momenta and generalized coordinates. In other words, g equals g of qk and pk, h equals h of qk and pk. And by definition, the Poisson bracket of the two functions is simply summing over all possible momenta, and then you take the partial derivative of g with respect to q, okay, multiplied with the partial derivative of h with respect to pk, subtract the derivative of g with respect to pk this time rather than qk over there, and h with respect to qk. So I'm a physicist and I've used this a lot, and it's a Poisson bracket, and I might make the mistake of calling it a commutator, because it is in fact very similar to what became commutators later on in quantum mechanics and in some fields of relativity. We also have similar structures that I also call a commutator. So if I make the slip in this talk and I call it the commutator instead of the Poisson brackets, please remember what I'm talking about. Hamilton then said, given this Poisson bracket, we can write down the equations of motion if we know what the Hamiltonian is. And so one of his big results was that he could actually canonize all the possible equations of motion, and you would see simply in terms of this commutator. So you had q dot of k for all the possible generalized coordinates is simply equals to the commutator or the Poisson bracket of qk with h, and similarly p dot is simply equals to p of k commuted or Poisson bracket with h. Okay, so it gave a very simple structure, or simple to remember and calculate structure, to the equations of almost all mechanical systems. Okay, and here the dot refers to the total derivative with respect to our time parameter tau. Okay, so further just written out, we have that f dot is effectively df d tau for any function that we are considering. Okay, and so you can see that over here we have our equations of motion in first order form, which is particularly useful if we want to integrate them on a computer, or if we want to start applying various theorems from dynamical systems to try and ascertain how these equations behave, and in fact look for constants of motion or anything else that may be of interest. Okay, so now what we're going to do is we're going to make use of this formalism and apply it to general relativity. I'm basically assuming that you don't necessarily know any general relativity at all. However, the only thing we need to get the geodesic equations out is to be able to construct the Hamiltonian that we then plug into the Poisson, into Hamilton's formalism to actually get out the equation of motion. So I'm going to give you some discussion of how we actually now construct that Hamiltonian that we use to get the equations of motion. So in four-dimensional gravity, we're going to say have at least four generalized coordinates and momenta. So k is going to be equals to 1, 2, 3, 4. And we call this 4 degrees of freedom of our Hamiltonian system. And we're going to call the generalized coordinates rho, z, phi, and t. So effectively a cylindrical coordinate system plus time. And with each generalized coordinate, we're going to have an associated generalized momenta, and I've just indicated it by p subscript the coordinate it refers to. So this then leaves us with 8 dependent variables. And now, if you can remember some of the results from Steve Strogatz's dynamical systems, we know that if we have one dependent variable, the result of the dynamical system is that it simply goes to fixed points or infinity. If we have 2 dependent variables, we still have fixed points infinity, but the nature of the fixed points are more general. In other words, we have stable fixed points, unstable fixed points, which can be nodes or spirals. But then, in addition, we can also have saddles and centers and things like that. So that's all that's possible in 2 dependent variables. If we go up to 3, we know that there are more possibilities. For example, we then have the possibility of limit cycles, where the Poincaré-Bendixson theorem gives us a way of actually proving that these things exist or not. And solutions we find then generally go to limit cycles or fixed points or to infinity. And so that's 2 variables. When we go up to 3, we have the possibility of strange attractors, one example being the Lorentz attractor, and a number of other attractors which we cannot otherwise find in 2. Okay, a Hamiltonian system always has an even number of dependent variables. So the simplest Hamiltonian system beyond 3 is then basically has 4 dependent variables, in which we can start seeing things like Hamiltonian chaos arriving if we can't find a full set of constants of motion. Okay, so 8 dependent variables is a lot, Okay, when we go past 4, we get things like Arnold diffusion in Hamiltonian systems that we can't get in 4. So 8 dependent variables, we're going to see a lot of potential complicated dynamical features. And what we're going to do now is try and simplify it even further so that we find the simplest unsolved problem, as it were. Okay, the way we construct our Hamiltonian is to make use of some of the fundamental fields in GR, namely the 10 metric functions. Okay, so to think about the metric, and we're going to assume all the metric functions are simply functions of coordinates or generalized coordinates only. So the metric is basically what encodes all the dispersion of the space-time. It can be viewed as a 4x4 symmetric matrix. That's why there are 10 components, namely the upper diagonal parts of this matrix. So it's 4, 3, 2, 1 adds up to be our 10 independent metric functions. So what the metric does is it gives us a rule of how to measure distance. And for the purposes of the talk, that's the only thing you need to kind of remember. And the way it does so is it makes use of an infinitesimal generalized kind of Pythagoras theorem idea, where you can say the distance is not simply dx squared plus dy squared plus dz squared as we normally do in 3 dimensions. Rather, we have increments in the generalized coordinates, and at each point we multiply it by the metric that simply says how much that increment influences the distance measured at that point. Okay, and this is possibly the biggest contribution that a secretary has made to General Relativity. I often make use of this convention to mean exactly what I've said here, namely, you drop all the summation signs just as Einstein's secretary did, and you simply, the first time it was adopted, and you simply infer that each index that you find below and above is repeated and sum over. That's repeated below and above. You have to sum over it. In other words, you have to sum over I and as well as J. Okay, and this is simply a compact form of writing out the sum. Now, for general relativity, the Hamiltonian, that we need to actually work out the equations for the particle motion can be constructed from this metric. So the recipe for constructing this Hamiltonian, and it's not a recipe in the sense that I'm giving it to you, you can rigorously prove that in fact it's the correct Hamiltonian. But the way we calculate the Hamiltonian in GR is we simply are given the metric with the lower indexes. We then compute the inverse of this metric, and we define it to be Gij with upper indexes. In other words, we simply take the inverse of this matrix Gij over there and then make a new one. And then we use that one, the G upper components, that are functions of our generalized coordinates only, and we define or we construct the Hamiltonian to be pk qk equals to a half the upper index metric times pi pj. Okay, and note that this thing is quadratic in momentum. So what we're going to do now is try and find a way to make the problem even easier. This is the Hamiltonian for a general 4-dimensional space-time. What we can do is we now want to try various things to pare down the number of dependent variables we're going to have in our final dynamical system. And so to do that, we're going to focus the discussion on stationary axisymmetric vacuum spacetimes. We call it SAV, and each one of these words basically permit us to make simplifying assumptions on the metric functions themselves that will simplify the problem we look at. And once again, as I said, we are going to start exploring the most complicated unsolved problem as yet. Sorry, the simplest unsolved problem as yet. So the specializations basically result in constraints on the metric functions. The stationarity assumption basically assumes that the metric function is not a function of coordinate time, meaning that the metric doesn't change over time itself. So in some sense, it's a stationary metric. The axisymmetric assumption is basically that the metric does not depend on the coordinate about the z-axis. In other words, it's rotationally invariant about the z-axis. In other words, there's no phi dependence in the metric functions. And the final assumption that we live in a vacuum space-time results in the field equations, the Einstein field equations Rij equals to 0, which then restricts the remaining metric functions to actually obey this property. So just as in Newtonian mechanics, we found that the gravitational field was sourced by the mass density, so too in relativity, the curvature of the space-time is fixed by the stress-energy tensor, and we are only interested in space-times basically where we explore the particle motion where there is no influence from the stress-energy tensor. In other words, there it's Ricci flat. So this is the assumption we make in vacuum, and if we make these assumptions, the most general metric we can write down, which can also be rigorously shown, is this SAV metric, and it looks something like this. Instead of now having 10 independent functions, we have 1, 2, 3, 4, 5. Okay, so it's a great simplification, and recall that g phi t equals to gt phi because the metric is always a symmetric matrix or a symmetric tensor. And these functions are now functions of rho and z only. Okay, so it's quite a dramatic simplification from the full general case for which that Hamiltonian holds, but it will make us possible for us to explore these things from a dynamical systems perspective and try a few things out using known factors about Hamiltonians and such. Okay, so now to construct the Hamiltonian, we have to take the inverse of this metric. Okay, and this is it written out, just 1 over g rho rho, 1 over g z z, and this full matrix over here, where k is simply the determinant of this matrix. So I simply can take a 2 by 2 inverse of this matrix to get the upper diagonal matrix over there. Sorry, the upper Gij components over there. So that's now all we need. The next step to get the equations of motion is we write down the full Hamiltonian. We simply put in this Gij q, in other words, this thing, into this formalism, and remember to sum over the repeated index, namely I and j. And if we then write it out, we simply get p rho g rho rho from this term, and from the next term we get pz squared gzz, and then the contributions over here, p phi squared gtt over k minus the cross diagonal components over there, 2 p phi pt g phi t over k. Important, it's combining both of them, so there's a 2 coming in there. And then we get the pt squared g phi phi over k. Next step, now that we have the Hamiltonian, is to write down the equations of motion. And to do that, we simply use the definition of our Poisson bracket. So the momentum evolution, which I'm going to do first because there's some nice simplifications there, is simply p dot, and I've renamed the index here mu because I was summing over k in the definition of my Poisson bracket. So simply p mu dot equals to the commutator or the Poisson bracket of p mu with h, and so we have it over here. Okay, so p mu h is equals to the sum over k of d partial p mu with respect to qk, which is 0 because p, the generalized momenta and coordinates are viewed as being independent in the Hamiltonian formalism. So this term vanishes, minus partial p mu partial pk, And this thing is non-zero only if mu is equals to k. So we make use of these two identities to simplify this Poisson bracket even further, and what we're left with is p mu dot is equals to minus dh, the Hamiltonian for the SAV spacetimes, partial q mu. Okay, the generalized coordinate of which you want the generalized momentous evolution. And so we can basically write it first, simplified further, because h has all its coordinate dependence basically hidden in the metric. We can simply write out, take the derivative of the metric, the upper metric itself, in other words, take the derivative of this thing, and there we have an equation. And explicitly, because we've assumed that the metric does not contain functions of time, in our stationarity assumption, we have that dh dt is equals to 0. And therefore, we can immediately integrate what pt is. It's simply a constant, and we call that constant minus e. And it actually, in fact, refers to the energy, or the local energy of the particle. Similarly, we assume that our metric functions over here are independent of the variable phi. So dh d phi is equals to 0. And therefore, we can directly integrate p phi, and we will call p phi Lz, in some sense, the angular momentum around the z-axis, which is also conserved. Okay, so it's been going very well. We've managed to integrate 2 of our 8 equations, so it simplifies things down. And but the remainder, we're not that lucky, and so here we have that p dot rho, or sorry, p rho dot is simply minus dh d rho, and pz dot simply minus dh dz. But it's still easy to calculate, because you can simply differentiate this whole matrix with respect to rho, and then contract it with a momentum vector, column vector, and a momentum row vector, and then you have the answer, and similarly with a z. Okay, because we simply are differentiating this upper matrix with respect to rho and z. And so now we have all the momentum equations. What we're going to do next is try and get the coordinate equations, and we go through the same process. We want to work out the coordinate evolution from Hamilton's equations. So we have q dot equals to q mu comma h, so the Poisson bracket of q mu with h, and we simply use the definition of our Poisson bracket, and we once again here have partial q mu with respect to qk, which is non-zero only if mu is equals to k, and partial of q mu with respect to pk, which is 0 because your conjugate or your generalized momenta and coordinates and momenta are assumed to be independent for the purposes of working out the Poisson bracket. So we have those two conditions, which now simplifies the q dot mu into dh dp mu, okay, which is also your generalized Hamiltonian equation. And what that does is that we can now simply write down, make use of this Hamiltonian h over here, taking the derivatives with respect to the momenta, for which it is only quadratic in it, and simply write down what the equations are like. So we have t dot equals to dh dpt, and we can simply write it out. Remember that there's a factor of 2 over here, so this thing is actually half the Hamiltonian. So dh dpt, let's look wherever pt appears. So there we go. So that would just be 2 times p phi g phi t over k, but we have to divide it by 2 because of that 2 in front. So, and then we have a minus sign in front, so that's our first term. Over here, derivative with respect to pt, it will be 2 pt g phi phi over k, but we have to divide by 2, so we're left with pt g phi phi over k. Similarly with phi dot, you can go through the same process. dh d phi, simply look wherever you have phi, differentiate there to give the first term divided by 2 because it's twice the Hamiltonian, differentiate over here with respect to phi, you're left with pt g phi t over k and a minus sign. So there that term is. Okay, and we can go on. dp phi is simply, dp rho is simply p rho over g rho rho, and z dot is simply dh dpz, which is pz over gzz. Okay, so here we have the 4 evolution equations for the coordinates, and we're going to combine that with the momentum equations we derived on the previous slide, and where we've already integrated 2 of them, so we're left here with 6 ordinary differential equations for t, phi, rho z, p rho, and pz. Now, the important thing to note is that because we've assumed the metric functions to be independent of time and phi, these guys don't only depend on rho z, p rho, and pz. Okay, and similarly over here, there's no influence of t and phi, so we can basically decouple these 4 equations, the p rho dot, pz dot, rho dot, and z dot equations, which gives us a 4 ODEs. We can solve them first, and then we can substitute what we got for what we got for rho and z. P phi and pt we know to be constant already, so we can basically substitute, after we've solved these 4 equations together, we can substitute the result in there and then solve these 2 subsequently in post-processing. So what we've effectively got through all these assumptions is a 2-degree of freedom Hamiltonian, but with 4 equations that we basically have to solve, or 4 dependent variables, which puts us beyond the category of knowing the answer exactly, but there are systematic ways of actually looking for constants of motion and checking whether those things have constants of motion and describing the geodesics using these equations. Another important thing to note is that beyond having just simplified it to 4 ODEs, we in fact have an additional thing that's typical of Hamiltonian systems, namely that the Hamiltonian is conserved along the trajectories. Okay, so we have the concept of conservation of energy, and what that is simply that h dot is equals to 0. So there are several ways of showing this. Possibly the most direct with the tools that you've been given is simply to go and differentiate h with respect to its coordinates momenta, and then using the chain rule multiply that with, say you say dh dpk times pk dot plus dh dpq plus pq dot, and you will be able to show using these definitions for p and q's evolution that h dot is in fact 0, and this means that we can set h equals to a constant, and we call this constant mu squared, different from the index used earlier or used over there, and we know we call this equals to -1/2 mu squared, where mu is interpreted as the rest mass of the particle in motion in this Hamiltonian. In the very special case where mu is equals to 0, we in fact have photon motion, and we will explore the features of these trajectories in greater detail later on. Okay, so basically what the conservation of energy does is, in addition to the 4 equations that describe the evolution of rho z, p rho, and pz, we know that p rho and pz always evolve in a fashion that this thing is equals to a function of only rho and z. So look, all the things entering over here are constants except gtt k, g phi t k, and g phi phi, but these are only functions of rho and z, so we can effectively say that this quadratic relationship where our momentum are basically squared divided by g rho rho for p rho squared, and gz squared divided by gzz is equals to a function always, everywhere along the trajectory, of simply rho z, e, lz, and mu. Okay, so what I will be doing now is giving you a feeling for what motion is possible using these geodesic equations for a SAV spacetime that is less well known. So the most well-known spacetimes are Kerr and Schwarzschild, which is the ones we expect astrophysically, but all the SAV spacetimes have effectively been solved and are known, and we can actually get a specific metric. In this particular case, it's a Manko-Novikov metric, and then use these equations, evolve them, and that will determine how particles move. In particular, I will be focusing simply on massive particles. In other words, mu is positive. Okay, so let's see. Okay, if I can get the movie going. Okay, so what I've done here is to give you a feeling of different type of motion, is I've taken a number of particles and put them in a stationary. In other words, I gave them no initial momentum in any spatial direction. The center of the Manko-Novikov black hole sits over here, and I've simply let them evolve or fall freely from rest into the black hole. So we can at least see it's an attracting black hole for most part as it falls in. So here they go. And now we're going to actually look at the space-time. This is just to give you an idea of the core, and these features I'll discuss later. It's in the nature of the space-time we're looking at. It's a space-time in which time travel is in theory possible. And then around the core, we're going to put a number of test particles that are all on, initially, at least instantaneously, on locally circular orbits. In other words, they have no radial component to their velocity at the start. And we're simply going to let them go and then see what they tell us about the space-time. So the black hole, or the strange thing at the middle, sits over there, and we can see that this inner orbit is decidedly odd, whereas the others are a lot more regular. And let's just watch it for a bit. Okay, so you can see that this thing looks chaotic, whereas the rest sort of very slowly go out, are not exactly ellipses, but well approximated by an ellipse. And let's just speed it up because this can get a bit tedious. And so we can see that these other orbits, I'll let you look at them one by one in a moment, but they behave in a very ordered fashion, not at all in the erratic fashion that the centralized one does. Okay, so this is looking from the top. You can see with the red orbit, this is looking also from the top. You can just see that, and this one is sort of a two-circle feature that then slowly precesses, and this guy looks like a lesser G figure. All of them highly ordered, very similar to what we expect from an integral system. Let's just look at the angular change of these orbits. This is now looking straight on from the side. Okay, this is an almost entirely equatorial orbit. Right. Thank you very much. That's all from me now. I hope this gives you a feel for how to quickly and derive the geodesic equations, that you can play with them yourselves. Subsequent videos will go into greater detail about how we actually analyze these equations, as well as about features of the space-time itself that we can actually learn by observing these trajectories. I'll just let the video finish.